Hello again. Now we're going to look in general at procedural blocks and particularly at flip-flops, and very specifically go over why I'm using that funny type of assignment called non-blocking assignment when building flip-flops. But first of all, I'll just remind you that in general, code like this at the top, and always at statement, maybe a begin and end after that if there's multiple statements after it, and then some series of statements. Quite often, if they're else or cases, but other things, is referred to as procedural code. And it's called such because just like in C, the code between the begin and the end is executed procedurally, that is in order. And I remind you that every time you assign a variable in a procedural block, it has to be a registered data type. The only synthesizable registered data type is reg, so everything assigned in this sort of block is of type reg. And that is very true whether it's an output of a flip-flop or register or not. This is an unfortunate aspect of Verilog, that it used this data type for things that weren't registers, but that is something due to the history of the language. So the procedural block is always executed when the item in parentheses up top here is true or changes in the appropriate fashion, and this is referred to as the sensitivity list. So let's get on to blocking and non-blocking assignment, or very specifically why I strongly recommend to always use non-blocking assignment, that is this type of assignment, when building flip-flops. So let's look at the definitions first. Blocking assignment, the normal type of assignment, is called such because the execution of this next statement is blocked. That is, this assignment cannot occur until the execution of the first statement is completed, and so on if there's more than two statements. That is, the statements execute sequentially, in sequence, as you would normally expect to see in a procedural block. This is exactly what you normally write in C. In contrast, in non-blocking assignment, the execution of the second statement is not blocked, waiting the completion of the first statement. That is, the statements execute as if they're being run in parallel. Or more specifically, all the assignments do not occur until the end statement is reached. And this is referred to as non-blocking assignment because of this non-blocking aspect. Let's look at what difference that makes in terms of actual execution of a small example piece of code. So let's say we have this piece of code, A equals B, B equals A, that is meant to be the output of flip-flops. So it's assigned in always at pos clock statement. Let's say A is equal to 3 and B is equal to 4 but before execution. Well, the question is, what are the values of A and B after execution with these blocking and non-blocking statements? I suggest you pause the video and consider what that might be. Well, you've done that, so let's look at the first one with blocking assignment. Well then, let's see. A equals B, B equals 4. Before the execution of this block, so A becomes equal to 4. Now the second statement is executed after the first one is completed. B becomes equal to A. Well, A was just assigned to 4, so B is now equal to 4. Again, this is normal procedural code. However, what this means explicitly is that B took the value that A would have after the pos clock event is over. Remember, everything between the begin and the end here for all the pos clock events are made to look like they're all happening at the same time. So what we're seeing here are the values of the outputs of the flip-flop, the Q outputs of the flip-flops after the pos clock event is over. And notice B is taking that next value of A, not the value of A that was stored on the flip-flop before the pos clock event. We'll come back to that in a moment. Let's do a similar, just execute the code for A equals 3, B equals 4 using non-blocking assignment. Okay, you've gone ahead and done that. The result is, okay, A is equal to 4, just like before, because B had the value of 4 before the rising edge clock event. But now B is equal to 3. That is, these statements essentially executed in parallel, behaved as if they executed in parallel. B takes on the value of that A had before the rising edge clock. That is, B is now equal to 3. Now let's draw the logic that each describes. And again, I suggest you pause the video and consider what this might be before I present the solution. Well, with blocking assignment, we've got this conundrum that this value of A here is not the output of the flip-flop. The output of the flip-flop does not change to the next value of A until after the pos edge clock event is fully evaluated. However, that's what B is taking here. Where is the next value of A in the actual schematic? Is it the input of the flip-flop A? That is, we're drawing something like this. The first flip-flop is correct, since the first statement in the series of statements here, A is equal to B. A is taking on the value of B stored before the pos edge clock event. That is, the value of B at the output of this flip-flop. When B becomes equal to A, B is taking on the new value of A. That value of A is not stored at the output of A. Until the pos edge clock event is fully evaluated, that output is still this value 3 here. But notice B took on 4, not that value 3. Where is that in the actual schematic, that value? Well, it's at the D input of A. So B has the input of B has to be connected to the input of A, which of course is being driven from somewhere else in the design. Let's look at the schematic for the non-blocking assignment. Well, now we see what we expect to see. A and B are assigned in parallel, essentially. They behave as if they're assigned in parallel, taking on the values of B and A that existed before the rising edge clock event. Where are those values? They're at the outputs of the flip-flops. So the input of the other flip-flop is connected to the output of each of the opposing flip-flops. This is what you'd expect to see if you saw this code. Whether you wrote it like that or like that, if I just put this up and say, if I put this up at the top here and said, draw the schematic, this is what you would have drawn. So the point is, to get what you expect to see, you should use non-blocking assignment, because non-blocking assignment captures the behavior of flip-flops. In the design, the flip-flops all change simultaneously. You can't model that correctly with blocking assignment because that implies some sequentiality. Only by using non-blocking assignment will you get the behavior that all flip-flops change simultaneously on the pos edge clock event. So always use non-blocking assignment when you're building flip-flops. I'd even suggest to you that even if you're building one flip-flop by itself, to use non-blocking assignment. Why? Because you might go and change the code later, and this encourages you to use a non-blocking assignment if you added more code to that flip-flop block. So this is why in all the examples to date I've used this non-blocking type of assignment when building flip-flops to encourage you to think that way, and of course in case you went back to those examples as the class progresses. So let's look at another example of this. Here I have the most straightforward way to write this particular piece of code, putting each flip-flop in its own procedural block. I'd like you to think about what the schematic for this would look like. Well, it would look like what we see on the right there. That is, B as an XOR gate as input, D as an OR gate as its input. The outputs of these flip-flops go on to drive the inputs of the last procedural block, with its AND gate as its input. If I simulated this for a couple of clock cycles, this is what I expect to see. Again, I'm modeling internal logic delay. I shouldn't actually do that if I want to be like what you will see in the simulator, where all variables would change at the same time. Right, so this is fine, and this would always work, and model what we expect to see. Let me ask you this question. If I put all three of these statements in one procedural block using non-blocking assignment, will this produce the same logic as on the previous slide? Well, the answer is yes, because the non-blocking assignment is capturing the parallel behavior of all these flip-flops. Remember at the start of this class when I did the revision notes, I remind you very explicitly that on the rising edge clock event, simultaneously for all the flip-flops in the design, the input gets transferred to the output. That is what the non-blocking assignment here very explicitly models. On the other hand, if we forgot to use non-blocking assignment and we use blocking assignment, would we get the same logic that I had 2 slides ago? The answer is no, I would not. Why is that? Well, B equals A hat C, D equals A or C. Well, these are fine. They'll both use the values of A and C that existed before the rising edge clock event. However, E gets assigned after B and D gets assigned, not simultaneously as in the non-blocking example. What's the values of B and D at this point in the code? Well, the values of B and D are going to have after the pos edge clock event is over. Where are those in the actual schematic? They're at the inputs of these flip-flops. So we don't get the schematic we had 2 pages ago. Now, procedural block assigning E is taking the values of B and D from the inputs of B and D, because that is what's being specified by the blocking assignment here. So it's very clear that if you use non-blocking assignment when describing flip-flops, you'll capture their essential parallel behavior, and thus you'll be describing what you would expect to see in a drawing if you did a quick schematic of the code that we've just been looking at. So always use non-blocking assignment for flip-flops. In contrast, always use blocking for combinational logic. And I'll illustrate this more in a moment. In combinational logic, there is a sequence of cascading events. We're not trying to model the intrinsic parallel behavior of flip-flops. The logic changes ripple through the block of combinational logic, producing sequences of changes. Also, I ask you not to mix them in the same procedural block. That has no meaning in synthesizable design. So let's look at the combinational logic example. Here I have 2 examples for combinational logic. Notice the always at star. So we're specifying combinational logic. A equals B and C, D equals A and E. Second statement uses A. Well, if these execute in sequence, this is pretty much what you'd expect. A changes, then D changes. That is, the input here is taken from the output of this gate. This is not a clocked gate, so we want the changes to ripple through the sequence of logic here. In contrast, what's happening on the left-hand side is a little messy. D here is using the value of A that existed before the always at block was triggered. Well, where is that value in the design? It's not at the output of the AND gate, because we want that. We're changing that. So it's somewhere else in the design. And it might even be, if this was the first time this block was triggered in a clock cycle, it might even be in the combinational logic in the previous clock cycle. There's no logic that corresponds to this, at least no combinational logic. We'd actually have to insert a flip-flop in the design, and we can't do that because we haven't specified one. So using non-blocking assignment for combinational logic doesn't make sense. Combinational logic does operate sequentially. This gate changes, then this gate changes using the new value at the output of the first gate. That is what you expect to see, so we use blocking assignment for when we're building combinational logic. If you have any doubt, then just draw the schematic associated with this and think about logic changes rippling through that schematic in the actual logic. So in synthesis, we essentially actually only have one type of register, that is a D flip-flop. However, in this page I do remind you of the various variants of the D flip-flop that are useful to us in certain coding styles. We might want to apply a reset, or have a reset signal distributed in the design that brings the design to a known state. Well, if that reset is low, and usually reset is active low, we want a certain value assigned to the flip-flop, in this case 0. So here I have a synchronous reset. The second one here is a synchronous reset because Q will only change on the pos edge clock event. That is, Q changing on the reset is synchronized with the pos edge clock event. Here I have an asynchronous reset because I put this OR neg edge reset into the sensitivity list. Well, this means if reset goes low, even away from a rising edge of the clock, then Q is reset. Purposes of this class, it doesn't matter much whether you choose to use asynchronous or synchronous reset. They're slightly smaller if they're asynchronous, but does lead to other issues higher in the design. You usually actually want to synchronize this somewhere in the design. Within a design group in industry, it would be specified which type you'd be using. Here I have a D flip-flop with enable, which you can also think of as having a mux in front of it. This is very similar to the many examples we've already seen so far. And here I have a synchronous clear and preset, which are possibly locally generated signals or signals coming from some controller that are just locally clearing or presetting the register. And these are always synchronous. Now this reset signal I talk about here is special, it's different. This comes from outside the design. And I encourage you to be very aware of this. That reset is some global signal intended to get the machine into a known state. It's not locally generated by you, the designer, and is not modified by you, the designer. I encourage you in your designs to have one signal called reset, which is an input to your design from the test fixture, and its sole purpose is to get the machine into a known state. You've all had a problem where your machine is frozen somehow or another, and you've had to power cycle it in order to unfreeze it. Power cycling might actually be holding down a power button. Sometimes it might even be a reset button. Or it might be some combination of buttons that gets the machine back into a known state. You've all had this experience with modern electronics. So I remind you, this is an external signal. And here I've drawn that very explicitly. I found this picture with this nice red button labeled reset. This is how things used to be. It's not common today. It's usually connected to the power supply. But nonetheless, it's a global signal from outside your design whose sole purpose is to get the machine into a known state. These days, it's actually usually associated with the power supply. What actually happens is, when you turn the machine on, the DC voltage coming out of the power supply ramps up. When it passes a certain value that's less than the normal supply voltage to the chip, the chip says, you're on a power up event here, and it sends a reset to the rest of the chip. This happens just before reaching the full swing of the supply voltage, the reset might take quite a while to actually distribute and execute. It tends to be a slow signal. It doesn't need to be synchronized with the clock, especially. And a few cycles later, by the time the machine most probably has reached the full power supply, you've now set the machine into a known state. So an obvious question is, which registers require reset? Well, some design groups actually specify in the design methodology that all registers must be reset into some state. However, strictly speaking, you really only need to do this for registers that determine the state of the machine. A very explicit example is the finite state machine state vector. In the finite state machine examples we looked at the beginning of this class, we always initiated the finite state machine into state 0, which is some sort of wait state for something else. And furthermore, in those finite state machines, there quite often were illegal states, which we don't want to accidentally initialize ourselves into. What normally happens with reset is all the finite state machines, the state vectors are set to some root state from which we get very predictable operation of the chip. And again, I remind you, this is not a designer-controlled signal. Reset comes from outside your design. Very explicitly, it comes from the test fixture. So that brings us to the end of this submodule. I encourage you to always use non-blocking assignment when assigning to flip-flops. This is because what you expect to see is what you get. For a similar reason, always use blocking assignment when describing combinational logic. Flip-flops operate in parallel. Blocking assignment within combinational logic within one combinational logic block, the data changes ripple through it. The earlier gates affect the later gates in the same evaluation cycle. I want you to apply a global reset signal to all registers that determines the machine's state. So finite state machines, possibly some counters, some status registers, etc. And I remind you, reset is a global signal that comes from outside the design. It's not one I want you to generate locally. If you need to have a clear, then call it clear. Don't call it reset. Reset's a golden signal. What I suggest you do now is move on to the submodule quiz for this particular submodule before proceeding to the next submodule. Thank you very much.